Hi, I'm Wim Bogaerts from Ghent University and IMEC, and I would like to thank the organizers for inviting me to talk about our work in programmable photonics. And today in particular, I'll be talking about actuators for large-scale programmable photonics. I should say that quite a lot of the work that we're presenting today has been done in collaboration in MORPHIC together with other partners like EPFL and KTH. Now, when we talk about photonic integrated circuits, we're thinking about different functions that we want to connect together on a chip, like wavelength filtering, modulation, light sources, detectors. And you connect everything together with waveguides. So the functionality of the circuit is not determined by the individual blocks, but more often by the way they are being interconnected. And so over the years, we've seen an evolution from very simple circuits where all the connections have been defined at fabrication time to circuits which become more complex in the sense that some of the functionality now becomes tunable or configurable, to circuits which contain multiple functions at the same time. Now, in the past few years, we've seen an evolution towards circuits that we could call programmable. The functionality is no longer determined in hardware by the connectivity, but at a later stage during operation by tuning all the individual elements in the photonic chip, and that shows how the paths can be routed. And we're seeing that evolution slowly towards what you could call a general purpose programmable photonic circuit, where you have a number of functional building blocks like modulators, detectors, waveguide ports that are connected by this completely reconfigurable circuit. And such a circuit can do waveguide routing through multiple paths. You can even fold back on yourself and route multiple paths at the same time. These can even go through the same coupler, and some of these couplers can also be configured not just as a bar and cross state, but also as a partial state, which allows you to do power splitting and even combining light again. And this is powerful because it gives you an interferometer that you can use to define wavelength filters, such as Mach-Zehnder interferometers or ring resonators. Now, the first demonstration of such a circuit was done by the Polytechnical University in Valencia and shows this 7-cell, 7-core circuit. Now, over time, we've seen a gradual increase. One of the things that you see is that this has a lot of electrical wires just to control it, and it only has 60 tuners. But we've seen circuits now scaling to hundreds of tuners, and we envision that a fully programmable large-scale photonic circuit will go up to 1,000 tuners or more. So we're seeing now an evolution towards these large-scale programmable circuits which require more and more tuning actuators. And the core element, the core tunable element that you need for these actuators is what we call a 2x2 optical gate. It's essentially a tunable element that can both control the coupling between the two inputs and the two outputs, but also their phase delay. So essentially it constructs a unitary matrix between the input and the output. And to implement it on a chip, you can, for instance, combine a tunable coupler with a tunable phase shifter. Or, alternatively, you could construct a Mach-Zehnder interferometer with one phase shifter in one arm to control the coupling, and then another phase shifter somewhere else in the Mach-Zehnder interferometer to control the phase. So we see that we need essentially two types of actuators. We need phase shifters and we need tunable couplers. Now, if you look at the circuit that I just showed before, this has 60 tunable elements. If you want to scale up to much larger circuits, you need to think about the type of actuators that you're going to use. First of all, you need really good actuators. They need to be small. They need to have a short optical length, which gives you a lot of freedom to construct optical filters. They need to have low optical loss and low electrical power just because the light needs to propagate through many of those and you need to drive many of those in parallel. And that automatically puts some constraints on your electrical driving circuits and the interconnections between your electronics and your photonics. And last but not least, it's important to realize that we want to integrate all of these actuators into a complete PIC platform where you also have the functions like modulators and detectors. Now let's look at some implementations for these actuators. If you want to integrate them in a full platform, you need to first start off from the platform. And in our case, we use the imec ISIP50G platform, which is a full-fledged silicon photonics platform that has all the bells and whistles like modulators, detectors, multiple layers of metallization and fiber interfaces. The cross-section looks a bit like this, which is very similar to those of many other silicon photonics platforms. So you have waveguides, you have doping levels to make modulators, and you have germanium epitaxy to build detectors. In this platform, there's already a number of ways to implement your actuators. You have, for instance, a way to implement heaters, or multiple ways even. Or you can use the carrier-based phase shifters that are also used for modulators. However, that last option is not very viable because carriers typically induce loss, and this is something that you really don't want if you want to cascade lots of these actuators. On top of that, we're also looking at alternative methods. One of those is to introduce birefringent materials like liquid crystal, or to use the semiconductor processes to actually make movable elements, microelectromechanical systems that move the material around. We're also looking at electro-optic materials like perovskites or polymers, but these typically have a fairly weak effect, so that requires a very long phase shifter, which is not attractive for our particular purpose here. So let's look at the most obvious one, heater-based actuators. They're typically quite simple. You have a waveguide, you put an electrical resistor next to it, which, when you send a current through it, generates heat. That can be done in metal, that can be done in doped silicon. What you typically get is this quadratic voltage response. The power is quadratic with the voltage or with the current, and an efficiency of approximately 5 to 30 milliwatts needed for a pi phase shift. That's quite a lot, even in a high efficient material as silicon. Now, in our ISIP50G platform, we have both types. We have the heaters based on tungsten metal, or we have heaters based on doped silicon. The performance of these heaters is very similar because it's entirely determined by the efficiency of the material system around it. So it's how much light or how much heat, is actually transferred from your heater to your waveguide and how much heat then leaks away from your waveguide. And overall, what you need to do is optimize the insulation and to minimize the heat capacity. So to make your heater small and well insulated. And already, like many years ago, this is 10 years old, MIT came up with this very elegant design of a very compact ring resonator with a heater that really drives down the power already to 10 milliwatts for a pi phase shift. And then this more recent design, for instance, gives us an efficiency of about 2 to 3 milliwatts for a pi phase shift by stacking all the waveguides very, very, very close together, so that all the volume that you're actually heating is also useful volume. Our heater uses a very similar approach here. So we have this kind of paperclip waveguide that passes through the same heated volume multiple times, and then we organized our heaters in segments in between the waveguides. And that way we can construct this 2x2 optical gate, with the big drawback that this has quite long optical path length. So if you want to make this more efficient, you need to go to tricks like undercutting the substrate to add more thermal insulation, or even removing the substrate locally altogether. And then you get these very nice freestanding heaters, which are very well insulated from the substrate. Now, heaters need driving, and so you typically want to use a digital to analog converter, which introduces some discretization errors, but you also need to take care of that quadratic response curve. So you need some adjustment to your driving scheme to get a fairly linear response. In practice, that's not very convenient because you want a linear phase response, but in the end you get this quadratic response. So you need to adjust your voltage ramp to linearize this system. A more elegant approach is to not use an analog driving scheme, but a digital driving scheme, by just sending pulses through the heater And if you send them fast enough, the heater basically just sees the average power, which is proportional to the duty cycle of these pulses. So this is quite linear. The only catch is that you need to be fast enough. So we're talking about pulses of 200 kilohertz or more, moving towards a megahertz. Now, there's another trick you can pull with heaters. You have essentially a symmetric response curve. So half of that is basically useless or redundant. So if you put a diode in front of your heater, you now make your heater only respond to the forward bias, and the reverse bias, it acts as a capacitor. So now you can use that reverse bias to drive a second heater. So you can essentially, in a gate, drive two different heaters with the same set of paths by just forward biasing it or reverse biasing it. And these are the 2 degrees of freedom that you can use to drive a single optical gate. You can even drive both at the same time. Just to give an example, in this case 2 ring resonators, each with a heater, they are time multiplexed using a digital signal. So you basically, half of the time you're sending pulses through one heater in forward bias, the other half of the time you're sending pulses to the second heater. And that way you can drive both heaters independently. And this scheme of multiplexing can be extended even further to matrix addressing, where you can drive n times n heaters using m plus n wires essentially. So for instance, this 1/16 splitter tree can now be controlled with only 8 contact paths. And that's actually quite convenient, because you can now, with a bit of electronic multiplexing, drive many more elements with just the same number of wires. And this shows the fabricated design. And here we show how we can progressively reconfigure this device by simultaneously driving multiple heaters. For instance, maximizing the power in output 1 or maximizing the power, in this case, in output 14. Now, heaters, while they're very easy to implement, do have a problem. I mean, they still consume power. So they make your chip hot and they can cause thermal crosstalk. So that's why we're also looking towards alternatives. And one of those is liquid crystals. Now, we've been dabbling with liquid crystals on silicon photonics for 20 years with some nice results. Liquid crystals are actually a very birefringent material. So depending on how you reorient their molecules, the light feels a very different refractive index. So by embedding your waveguides in a liquid crystal cladding and then applying a voltage, you can now reorient the liquid crystal molecules and change the refractive index. And this gives very powerful actuation, like in this case with a ring resonator that we can actuate over multiple free spectral ranges with the liquid crystal. But we still need to introduce that liquid crystal in the rest of our technology platform. And so for that we need to open up our metallization stack on top of the waveguide and then deposit the liquid crystal in there, which you can do, for instance, using inkjet printing. You also need to be able to drive it from within that platform. So that means that you need, in this case, a lateral electrode where you contact the liquid crystal from the side and reorient it between parallel to the waveguide and perpendicular to the waveguide. And the result, like this, you see the liquid crystal embedded in that little cavity. And in this case, with a 50 micron long phase shifter, we achieve a 0.8 pi shift with only 5 volts driving. Now, another alternative way of actuating that we're looking into is MEMS actuators, essentially movable elements. Now, the idea of combining MEMS with photonics is nothing new. After all, it's a mechanical effect, it's going to be very strong. It's also electrostatic, so it's low power, and you can even do mechanical latching, which makes it non-volatile. Now, the easiest way to do MEMS is just moving material around. Essentially, making a tunable coupler is nothing more than having 2 waveguides close together, which you then move further apart, either using horizontal displacement or vertical displacement. You can even come up with schematics where you have 2 waveguides in stacked layers together that you move closer and further apart. Making a phase shifter is actually not much different. Only you just replace one of the 2 waveguides with a much narrower beam that acts as a perturbation of your original waveguide, essentially inducing a phase shift. Now, in the MORPHIC project, we've brought together 6 partners from Europe to build such MEMS devices, but not just on their own, but embedded into the existing ICIP50G platform. So for that, you need to start from your open waveguides, but we added a layer of protection so that we can selectively and locally remove the underlying oxide, basically creating freestanding photonic MEMS membranes. Now, this gives us, first of all, very nice SEM pictures, but most important, it gives you these nice waveguide geometries like these suspended rib waveguides or these suspended wire waveguides. And you can see this little ski here parallel to the waveguide. That's essentially a phase shifter. Let's look a bit closer. This is our standard phase shifter that we're using now and which will also be presented or has been presented at this conference by Pierre Iddinger. Now, you see the waveguide path of the light going in and out of the MEMS, but and next to the waveguide you see that there's a narrow silicon beam. That narrow silicon beam is suspended and is by folded springs and is residing on a shuttle that can move back and forth closer and further away from the waveguide, actuated by these comb drives. That means that as your beam is close to the waveguide, you have a high refractive index, but as you are pulling it away from the waveguide, your index becomes systematically lower. Now, to test this device, we've embedded it inside a Mach-Zehnder interferometer, and then we measure the transmission. Now, the theoretical modeling predicts that for a 30 volts actuation, you can get a pi phase shift with a 60 micron length. In reality, it turns out that it's even more efficient and that we get this performance already at 20 volts. But you can engineer the width of the waveguide, the width of the beam, and the spacing between the waveguide and the beam to either have higher efficiencies. So, however, if you make your waveguide too narrow, which increases your efficiency, in this case, you get a 2 pi phase shift for 25 volts, that comes at the price of a somewhat higher insertion loss, because your light now feels much more this perturbation of this phase shifter. Still, we see that we have an insertion loss of around 0.2 dB for this device, which is quite good, and which puts it really in the corner of high efficiency here of these of this performance plot of insertion loss versus the length required to achieve a pi phase shift. We can use the same platform to build tunable couplers, and these are all based on this kind of basic building block, which is a broadband freestanding directional coupler. Now, this device gives you is engineered to give you a fairly broadband wavelength response. So with little variation, and now you can integrate this device into these movable MEMS elements. So one example, which will be presented next month by Yuji Takabayashi at the IEEE Transducers conference, is this device where you embed this movable directional coupler into a horizontal waveguide. And so in the default state, the coupler is very close together and you basically couple all your light to the drop port, while if you pull on the waveguide, essentially your coupler is moved away and you couple all the light to the pass port. And this looks pretty nice under the SEM, and if we characterize the device, basically what we see is that indeed we can go all the way from high coupling, where the waveguides are close together, to low coupling or zero coupling, where the waveguides are further apart, and even more than that. And we can use this same coupler, for instance, also in a vertical actuation. So this example of a switch based on the same device, again by EPFL, where you pull down your coupler to the substrate by applying a voltage between your your waveguide layer and your coupler. You pull it down to the substrate and basically can switch from drop to pass. Again, this is the device, and if you look at the transmission characteristics, you see that thanks to the weak springs, you get a very strong actuation with an extinction ratio of about 16 dB with only 5 or less than 5 volts of actuation. And you can make these devices even smaller. For instance, you can make a very, very tiny switch which has basically a rocking pin that connects either to port 1 or port 2 by applying a voltage over electrode 1 or electrode 2. And so that takes a bit of engineering because you need to make sure that the device moves properly, remains in plane, and does not attach itself to one of the electrodes. It doesn't make physical contacts to the electrodes. But once you've done that, and you've optimized the coupling area between the two tips to have maximum optical coupling, you see that you can get a switch with a very high extinction ratio. So either with a positive or negative actuation on electrode 1 or electrode 2, you can get like a 25 dB extinction ratio between the one port and the other. And that for a very tiny movement of waveguide. Now, one of the problems of MEMS is that you have freestanding waveguides. So you need some way to protect these MEMS from the outside world if you want to deploy this in like real applications. So in the project, we also developed a technique to do capping at wafer scale. So to basically cover all the MEMS devices with a silicon lid that hermetically seals it from the environment. And so while these devices have, you see there's like an aluminum ring around it, each device, which is used as a sealing ring to put on these silicon lids. And so this is not a Photoshop, this is an actual silicon lid on top of our devices. And this is done on wafer scale, 100 millimeter wafers at this point, where all the lids on all the devices are attached simultaneously. Now this addition to the ISIP50G platform of MEMS devices gives us an entire library of components that we can now use to make these programmable photonic circuits. So we have our tunable coupler, we have our phase shifter, and we can now bring everything together. And so one of the demonstrators that we recently fabricated, but that's currently still being assembled, has these 24 hexagonal cells combining tunable couplers and phase shifters using these MEMS devices, in total 200 actuators. So you get this kind of non-uniform layout, but if you connect these together, you get effectively a hexagonal mesh like I showed earlier. But of course, this takes quite a bit of space on a chip. So you can see that this circuit takes a sizable fraction of a 22 by 22 full field silicon photonics chip. Now the challenge with such a chip is to connect all these elements to the outside world. So for that, in the MORPHIC project, we also came up with a solution to package these. So to connect such a large chip up to 72 fibers, but also have the high frequency input and output to the modulators and detectors, and to connect up to 3,300 drivers to our silicon photonics devices. And for that, we designed this regular grid, which can be used in the future also for other chips to basically contact our MEMS programmable circuit. And the packaging around it is essentially based on a ceramic interposer which fans out all these 3,300 connections to the outside world. And so you can connect them with flex connectors to whatever driver electronics that you need. So that brings me to the end of my presentation. What about actuators for programmable photonics? Well, first of all, we need good actuators with short optical length and low optical loss and low electrical power, and we need to integrate all of that in our PIC platform. So the solutions that we're working on is to make better heaters on one hand, the conventional approach, but also look at more disruptive approaches like liquid crystal and waveguide MEMS that can really make a disruptive difference in the performance of these actuators. Now, that being said, I would like to thank all the people contributing to this work, also the MORPHIC project and my ERC project PhotonicSWARM for the funding. And I would very much like to thank the entire team, and I hope that and soon we can really go back to collaborating in real life beyond Corona times. Thank you.